Welcome back, listeners, to The Deep Dive.
Great to be here.
Today we're digging into a research paper, really getting into the weeds on the mathematics behind deep neural networks.
That's right. We're looking at their geometry, specifically through something called critical points.
Yeah, so our mission for this deep dive is to unpack this. What are these critical points in, neural nets? Why should you care? And crucially, how does their number change, especially as these networks get bigger and deeper?
It's all about understanding the underlying structure, the foundational math that makes these things tick.
And just a reminder for everyone listening, you can always find links to the papers we discuss and stay updated on the latest research over on our webpage, which is linked in the bio. We try to keep you right at the cutting edge.
Definitely worth checking out.
So let's set the scene. The paper focuses on deep neural networks, right? Specifically wide ones, at the point they're initialized.
Exactly. And the key idea, the starting point, is that in the limit when they get infinitely wide, their output function starts acting like a random field on a sphere.
Okay, hold on. Random field. That sounds
Yeah.
pretty abstract. What does that actually mean for a network? Why view it that way?
It does sound abstract, but it's a super useful perspective. Think of the network's output, maybe for all possible inputs, as this kind of landscape. A random field just means the heights and slopes across this landscape follow certain statistical rules.
Okay, like a bumpy surface with random bumps.
Sort of, yeah. And the power of thinking about it this way is huge. It unlocks this whole mathematical toolbox. Techniques used in, say, cosmology to study the cosmic microwave background. We can adapt them here.
Wow. Okay, so it connects neural nets to other complex systems.
Precisely. And within that landscape, these critical points are really important features.
Right, the main topic today. So what are they exactly in this landscape picture?
They're simply the points where the landscape is flat, where the gradient, the slope is zero. So think of the very top of a hill, the bottom of a valley, or even a saddle point on a mountain pass.
Peaks, valleys, saddles.
Exactly. And counting them, understanding their distribution, gives us a handle on how complex or, wiggly that function landscape is.
And the paper uses something called the categorized formula to count them.
That's the one. It's a classic result from studying Gaussian random fields. It's designed to do exactly this: count critical points or level crossings, things like that.
But there's a catch, right? It doesn't always work.
Well, yeah, the standard categorized formula needs the random field, our function landscape, to be sufficiently smooth. No sharp corners or instantaneous jumps.
And this is where this CRI thing comes in, the covariance regularity index.
You got it. The CRI is the key. It's a single number calculated from the network structure, specifically its covariance function, that tells you exactly how smooth that landscape is.
Okay.
And the paper shows there's this really sharp difference, like a cliff edge, based on the CRI value.
What's the split?
If the CRI is greater than 2, the landscape is smooth enough. Mathematically, it's C2 almost surely, like, smoothly rolling hills.
Okay, differentiable twice, basically.
Right. And in that case, the regular case, the classical categorized machinery works perfectly. You can actually calculate the expected number of critical points.
But what if it's not greater than 2?
Ah, that's the irregular case. If the CRI is strictly less than 2, the landscape isn't smooth enough. It might have sharp kinks or corners.
And this happens in real networks.
Oh, absolutely. The most common example the paper points out is the ReLU activation function. Very widely used. It's CRI. It's 32. Less than 2.
So for ReLU networks, the standard math, it just breaks.
It breaks down. You can't directly apply the classical categorized formula to count critical points in the same way. It's a fundamentally different scenario.
Okay, that's a huge distinction. Let's stick with the regular case for a moment, where CRI is greater than 2. The math works. What does it tell us about how the number of critical points changes as the network gets deeper?
More layers, right?
This is really the core theoretical result. They found that the scaling behavior, how the expected number of critical points grows with depth, let's call it L, is governed entirely by one simple parameter.
It's one number. Yep. Derived from the network's covariance structure. They call it kappa prime at 1. It's related to the derivative of the covariance function.
And depending on that number, things behave differently.
Massively differently. Theorem 3.3 in the paper lays out 3 distinct regimes based on kappa.
Okay, what are they?
Regime 1. Oh, if a she1 is less than 1. In this case, as the network gets deeper and deeper, the expected number of critical points actually converges to a constant value.
It levels off. Adding more layers doesn't keep adding complexity in this way.
Exactly. The geometric complexity measured by critical points saturates.
Okay, what's regime 2?
If chi1 is exactly equal to 1, this is a critical point itself in a way. Here, the number of critical points grows polynomially with depth L, specifically like L to the power of D2, where D is the dimension of the input space.
So steady, predictable growth. Not exploding, but not leveling off either.
Right. And then there's a third regime.
Let me guess. Kyo is greater than 1.
You got it. And this is where things get wild. If A1, the expected number of critical points, grows exponentially with depth.
Exponentially. Whoa.
Yeah, like K1 to the power of L times that polynomial factor LD2. So adding just a few layers can cause the number of peaks, valleys, and saddles in the function landscape to absolutely skyrocket, a potential explosion of complexity.
That's incredible. That one parameter,
Yeah.
K1, dictates whether complexity plateaus, grows steadily, or just explodes.
It really is. And what's also cool is that this classification based on geometry counting critical points actually matches up perfectly with classifications other researchers found by looking at purely spectral properties of these networks.
So the geometry and the spectrum are telling the same story about depth.
It seems so. It hints at a really deep connection there.
Now, they also looked at a slightly different scenario, didn't they? Not just all critical points, but ones above a certain threshold.
They considered critical points where the network's output value itself is above some level, say U.
Did that change the scaling behavior?
Interestingly, no. Theorem 3.4 shows that for the regular case, CRI2, the exact same three regimes based on CAR1, convergence, polynomial growth, exponential growth still hold.
So the fundamental behavior with depth is the same.
Right. The only difference is the overall number is scaled down by a factor related to that threshold. Higher threshold, fewer points above it, but the way that number scales with depth L remains dictated by CAR.
Okay, fascinating.
Yeah.
But let's go back to that other world, the irregular one, where CRI is less than 2, the world of ReLU. The math broke down. So what do we know about critical points there?
Yeah, this is where the paper leans heavily on numerical experiments, on simulations, because the standard theory doesn't give you a nice formula.
And what did the simulation show for ReLU networks?
Something really suggestive. They basically mapped out the network's output landscape on the input space, and they did it at different levels of detail, different resolutions.
Wow.
And what they found for ReLU was that as they increased the resolution, as they looked closer and finer, the number of critical points they detected just kept going up significantly.
So unlike the regular case, it didn't seem to settle down. The closer you look, the more wiggles you find.
That's exactly the interpretation. It strongly suggests that for these irregular activations, like ReLU, the true number of critical points might actually be infinite.
Infinite, wow.
Or at least the geometry might be much wilder, maybe fractal-like, having a non-integer dimension, as the caper conjectures. It's a stark contrast to the regular cases where the number is finite and behaves predictably with depth.
That sounds fundamentally different. How well did the simulations back up the theory for the regular cases, too?
Oh, very well. They ran Monte Carlo simulations using activation functions designed to fall into each of the three APO regimes.
And they saw the convergence, polynomial, and exponential growth.
Clear as day. The simulations nicely confirmed the theoretical predictions from Theorem 3.3 for the regular activations they tested, like Gaussian or TANF variants.
So the numerics lined up with the theory where the theory applied.
Exactly. And they also really highlighted the contrast. You could see the number of critical points stabilizing or growing predictably for the regular activations as resolution increased, but for ReLU, it just kept climbing.
Really driving home that regular distinction.
Definitely. The simulations were crucial for giving insight into that ReLU case where the analytic tools fell short.
Were there any limitations mentioned with the simulations?
Just the usual practical ones, really. Simulating very deep networks accurately gets computationally expensive. So while they saw the exponential growth start, validating it for extremely large depths numerically has challenges with finite precision and things like frequency truncation, standard numerical issues.
Right, makes sense. Okay, so let's recap this deep dive. We've journeyed into the geometry of neural networks at initialization.
Yeah, we saw this covariance regularity index, the CRI, acting like a switch. Greater than 2, things are smooth, classical math applies. Less than 2, like ReLU, it doesn't.
And in that smooth case, this single parameter is king. It decides if the number of critical points, those peaks and valleys, levels off, grows polynomially or explodes exponentially as you add layers.
Converge, polynomial, exponential, 3 distinct fates based on one number.
And then for the irregular case, like ReLU, the simulations paint a picture of potentially infinite critical points, maybe even fractal geometry. A much wilder landscape.
A really dramatic difference suggested by the numerics.
So pulling back, what's the bigger picture here? Why does counting these points matter for understanding deep learning?
Well, I think it provides this really interesting geometric lens on network complexity right from the start, at initialization. The number and arrangement of these critical points tell you something fundamental about the kind of function the network is set up to represent.
And the fact that different activations lead to such drastically different geometric behaviors.
Right. The contrast between the sort of well-behaved complexity scaling in regular networks and the potentially infinite or fractal complexity hinted at for ReLU, it's huge. It begs the question, how does this initial geometric complexity influence the entire learning process?
Does a more complex initial landscape make optimization harder?
Mhm.
Or maybe easier in some ways? Does it affect what kinds of data the network can effectively model?
Exactly. How does this geometry relate to optimization dynamics, to generalization, to the network's capacity? Understanding these connections, bridging this initial geometric picture with the dynamics of learning, that feels like a really crucial direction for building a deeper, more complete theory of deep learning. It's a fascinating puzzle.